Hey, and welcome to The Explainer. Today, we are going to unlock one of the biggest secrets in all of chemistry. We're talking about a single concept that lets us count individual atoms just by weighing them. It's the bridge between the world we can't see, the world of particles, and the world we can actually measure. So how on earth is that even possible?
It really all starts with this one simple question. Think about it. You can't just put a single atom on a scale, right? You can't count out molecules one by one. It's impossible. So how do chemists come up with these super precise recipes for, everything from life-saving drugs to the advanced materials in our phones? How do they know exactly how much of one thing they need to react with another?
Well, the answer is a really clever trick. It's a special unit, kind of like a baker's dozen. You ask for a dozen donuts, you get 12. Simple. But when a chemist asks for a mole of atoms, they get this absolutely mind-boggling number. That's a 6 with 23 zeros after it. This right here is the secret key to counting the uncountable.
So, that magic number? Yeah, it's got a name. It's called Avogadro's number. And trust me, it is the cornerstone for how chemists connect the tiny, invisible world with the big, visible one.
Okay, so what is a mole? Like in textbook terms? Just think of it as a specific number, a standardized amount. So a mole of anything, doesn't matter if it's carbon atoms, water molecules, or even donuts. It's the amount of that stuff that has exactly 6.023 times 10 to the 23rd particles. Let's just pause for a second and try to appreciate how huge this number is. It's so ridiculously big that if you had a mole of marbles, it would cover the entire surface of the Earth in a layer over 50 miles deep. Wow, that's the scale we're talking about. Even in just tiny bits of stuff.
But look, this giant number isn't just some cool trivia fact. The mole is actually a super powerful tool. Think of it like a chemist's Swiss Army knife. It's got these three main superpowers that let us link that invisible world of particles to stuff we can actually measure in a lab.
Okay, superpower number 1, connecting moles to mass. This is so cool. The mass of 1 mole of any substance in grams is exactly the same as its molecular mass. So take water, H2O. Hydrogen's mass is about 1, oxygen's is 16. So you've got 2 hydrogens plus 1 oxygen, that adds up to 18. And guess what? That means 1 mole of water weighs, exactly 18 grams. How neat is that?
All right, superpower number 2 is basically its whole reason for being. 1 mole of anything, anything, always has Avogadro's number of particles. So 1 mole of water has 6.023 times 10 to the 23rd molecules. 1 mole of pure iron, it's got that exact same number of atoms. It's our universal counting number.
And then there's superpower number 3, and this one's a special trick just for gases. As long as you're at what's called standard temperature and pressure, think 0 degrees Celsius and normal air pressure, 1 mole of any gas will always fill up the same amount of space, exactly 22.4 liters. Super handy.
Okay, so we have this awesome tool. Now, what do we actually do with it? Well, this is where we get into something called stoichiometry. I know, it's a big fancy word, but all it really means is reading chemical recipes. So take a look at this chemical equation. Yeah, I know, it might look a little intimidating at first, but now that we understand the mole concept, it's really just a recipe. See those big numbers out in front? The coefficients? That's the key. They aren't talking about single atoms. They're talking about moles.
So this equation is literally our recipe, and it's giving us the exact ratio of ingredients we need. It's telling us that for every 1 mole of phosphorus we use, we need to add 5 moles of nitric acid. If we do that, the reaction is going to make exactly 1 mole of phosphoric acid, 1 mole of water, and 5 moles of nitrogen dioxide. See? It's all about those mole ratios.
All right, that's enough theory for now. Honestly, the best way to really get a handle on the mole is to put it to work. So let's solve a couple of chemistry puzzles and see these superpowers in action, shall we?
Okay, let's start with a nice, straightforward one. We're going to use that moles to mass superpower. The puzzle is this. Calculate the mass of 1 mole of sulfuric acid. All we have to do here is add up the atomic masses for every atom in that molecule. So we've got 2 hydrogens, and they're 1 each. We've got 1 sulfur, that's 32, and 4 oxygens at 16 each. You add all that up, and you get 98. And there you have it. 1 mole of sulfuric acid weighs 98 grams. This is a perfect example of that direct link between the mole concept and a mass you can actually measure on a scale. Okay, you ready for a real stoichiometry puzzle now?
This time we're starting with an amount in grams, and we need to figure out how much product we'll get, also in grams. This is where we have to combine everything we know about moles and our chemical recipes. Okay, let's break this down. So, what are we given? We've got 6.2 grams of phosphorus. And what do we need to find? The mass of phosphoric acid that gets made. The bridge connecting these two things is our chemical recipe, which tells us that all-important ratio, 1 mole of phosphorus makes 1 mole of phosphoric acid. That's the key.
So, first step, we use our superpower to translate everything into grams. 1 mole of phosphorus is 31 grams, and we figured out that 1 mole of phosphoric acid is 98 grams. So our recipe is telling us that 31 grams of our starting stuff makes 98 grams of our final stuff. From there, it's just a simple ratio to figure out what 6.2 grams will make.
And the answer is 19.6 grams of phosphoric acid. See what we did there? We used the mole concept to translate from grams into the language of the recipe, and then we translated right back into grams. It's just that powerful.
And you know the really cool thing is, we could use this exact same logic to figure out anything else in that equation, like how much nitric acid did we need, or what volume of gas was produced. Once you get the hang of converting things to and from moles, you can solve pretty much any of these problems.
So why does any of this matter? I mean, why is this one concept so incredibly central to all of chemistry?
Well, it's because the mole is that essential bridge we talked about. It's the thing that connects the theoretical world of single atoms and molecules, things we can only really imagine, to the practical world of grams and liters, things we can actually weigh and measure and mix in a real lab. It's what makes chemistry a real measurable science.
From designing new medicines to creating next-generation materials, understanding this one single concept is what allows scientists to control and build our world, molecule by molecule. It's what turns chemistry from something that looks like magic into actual engineering. So the only real question left is, what will you create?